So today's lesson is on the metric system and significant figures. These are things, at least with the metric system, that you should be familiar with and have heard about in middle school math, and you use a little bit of this in biology, and you've done a lot with it in middle school science. So I hope that you are familiar with it, but I'm going to go over some of the concepts associated with the metric system so that you are comfortable with it. And then we're going to talk a little bit about significant figures, or sig figs, so that you understand when we have to use sig figs in class. That's what we're talking about. Okay, this comes from Chapter 2, Sections 2 and 3 from the textbook, so if you need to reference those materials, that's where you can find it. Alright, so let's talk about the metric system. It is a worldwide system of measurement, although we don't typically use it in the United States as far as in general population, but in science everyone uses the metric system. It's a way to talk universally about a unit. So it doesn't matter where you're from. If you talk about, something has a mass of 14 kilograms, then everybody knows exactly in science what you are talking about. Whether they're from Japan or Russia or, South Africa, whatever, any of them will know what 14 kilograms means. Alright, so we call this system the metric system, or the SI system of units. SI stands for Système International, which is French for International System of Units. So what is the metric system? Well, it's a system that's based on the number 10. We, in the United States, don't tend to use the metric system. We use what's called the standard, or the English system. The English system has units like inches and feet and yards and miles, and sometimes those things get confusing because when you're trying to change from inches to feet, well, you got to take into the fact that, oh, well, there's 12 inches in a foot, and then there's 3 feet in a yard, and when you try to get to miles and you want to know how many inches that is, well, you really got to do some math, because you got to go, oh, well, there's 5,280 feet in a mile, and each foot has 12 inches, and it makes it complicated to do the math. There's lots of other things that make things complicated in the English system. For example, weight is pounds or ounces. And so if you said something was 4 ounces, well, in weight, that's how much it weighs. But there's also an ounce unit that's a measurement of volume. So you can say a cup, a liquid measure cup, is 8 ounces, or 2 cups are 16 ounces. And then you're like, whoa, is that its weight or is that its volume? And so that starts getting things complicated. So the metric system simplifies all that and gives you units, and everything is based on a relationship of 10. Alright, all measurements represent quantities, which is something with magnitude, size, or amount. So the unit, milliliter, that's the unit of measure, and it represents volume, which is a quantity. Alright, so here are the 7 base units for the metric system. Some of these we're going to use a lot, some of them we'll use occasionally, and some of them we will never use. So, what are they? Well, there's the basic units that everything is measured off of. And the first one is called a mole. A mole is one we're going to use a lot. Once we get to Chapter 3, we'll learn more about what is a mole. But keep that in mind. A mole is an amount of a substance. Okay? So it's like a number that represents a certain amount of substance. For example, it's like a dozen. What is a dozen? Well, a dozen donuts is 12 donuts. So a mole is so many of a certain thing. It's kind of the same idea. We're going to use a mole a lot and do molar conversions, and that helps us with chemistry. Mole is a very specific thing to chemistry, and no, it's not the animal that we're talking about. Alright, the next one is a mass unit. That's kilograms. Now, we tend to think of in terms of grams, but the actual base unit is called a kilogram. Temperature is Kelvin. For chemistry, the temperature, and for science, the temperature scale is called the Kelvin scale. You may have never heard of that. You've probably heard of the Fahrenheit or maybe even the Celsius scale, but not heard of the Kelvin scale. We will use the Kelvin scale, and we'll learn about how you go from Celsius to Kelvin. It's pretty easy, but we'll use this unit of measure more when we get much further on into the course. Seconds, that's the base unit for time. This is not a specific metric system unit because seconds, minutes, hours, days, years, that's not based on a unit of 10. That's based on how long it takes the Earth to orbit around the Sun. So this one is not a base unit of 10 part of the metric system, but it is the base unit in the metric system. You could say milliseconds or kiloseconds or hectoseconds. You could say that, but we tend to use minutes, hours, days, years, that kind of thing. Alright, an ampere. An ampere is a unit of electric current. We will not use this in our class. But if you take physics or if you take AP chemistry, you will run into amperes. And so an ampere is a measure of electric current. Meters, that's the unit for length. Definitely going to use this one. We'll be using it a lot. Candela is a measurement of luminous intensity. Think of a candle. It's how bright it is. And so candela is the base unit for the metric system, but again, we're not going to use this. So which ones are we going to use? Well, we're definitely going to use moles. We're definitely going to use kilograms. We're definitely going to use meters here, right, pretty quickly. We're going to use seconds, and then later on in the course, we're going to use some Kelvin measures. So keep those things in mind. Those are the 7 base units of the metric system. And then everything else is derived off of that. So how do we change between units? Because that's what you need to be able to do. Basically, when you are looking at the metric system, all of these words are prefixes that represent numbers. They have meanings in Latin. All right. So one that you're probably familiar with is kilo. Kilo in Latin means 1,000 or 10 to the 3. Same thing. Those are equivalent numbers. Hecto or hecta means 100. All right. Deca, as in decade. A decade is 10 years. So deca means 10. All right. Those numbers you're probably familiar with. You've done those with the metric system. This is where 1 is. We're going to call that our base. All right. Then we move to the smaller numbers, numbers that are less than 1. Deci is 0.1, so think decimal. There's your first decimal number. Centi is 100th, or 0.01. Milli is 1,000th, or 0.001, or 10 to the negative 3. And those are ones that you've used before. So most of us have become familiar with these numbers between here and here. And what's nice about this is each of these has a relationship of 10 to the 1. Difference between this and this, and this and this, and this and this, and deci and centi and milli. All of this is a relationship of 10 to the 1. So when you look at this to this, it's 10 to the 1. Or this to this, it's 10 to the 1. They have a relationship of 10 to the 1. All right. These other ones that fall out of this little bracket, some of these you've heard of before. Tera, giga, mega. You've probably heard of those in terms of computers. Megabytes, gigabytes, or if you have a really fast computer with a lot of storage, that's terabytes. All right. Now, each of these has a slightly different relationship. These, and we're going to put a little line here, each of these has a relationship of 10 to the 3. 10 to the 3 difference in each of those steps. And down here, when you're getting really small, same idea. Here's our barrier, and these also have a relationship of 10 to the 3. micro, nano, and, well, picos down here. You only use these when you're talking about really, really small things. So things on the microscope or things that you measure that are really, really small, micrometers, nanometers, picometers, those are really, really small. So like sizes of bacteria and things like that, that's where you get these. So how can we remember these units and know these units and be able to convert between these units? Well, I have a little saying, and you've probably heard it before, and it just represents each of these units here between these two brackets. It's kangaroos, hop down, mountains, drinking, chocolate, milk. Now, what goes right here? Well, this is your base unit, all right? So an example of a base unit would be meters or grams or maybe even liters. Base units are right here. So if I wanted to go from kilometers to meters, which would be right here at the base, then I would count and look at their relationship. So what's the relationship? Well, there are 10 to the 3 meters in a kilometer. All right. Now, how am I going to know that? Well, to go from kilometer to meter, I have to count 3 tens. 1, 2, 3. And so I can say that 1 kilometer is 10 to the 3 meters. All right. Well, how many millimeters is that? We'll keep going. All right. Let's make the kangaroo hop. The kangaroo is going to hop from kilo down here to milli. 1 kilometer, and it takes 1, 2, 3, 4, 5, 6. There are 10 to the 6 millimeters in a kilometer. All right, so what you do is you make a reference to the largest, how many of the smaller things are in the larger thing. And you just count how many spaces they are different from each other. And that helps you get through doing the math with conversions. So here's our nano, here's our pico. Just keep in mind, once you get out of this area, it's 10 to the 3. For Gen Chem, we're just going to deal with the kilo, hecta, deca, base unit, deci. We're just going to deal with these 10 to the 1 hops. For pre-AP, we're going to go a little bit higher and a little bit lower, and we'll practice a lot with this, so I want you guys to be comfortable with it. All right, so let's do some examples of conversions. Let's talk about converting between units and do some math examples. So we have to remember how our units go. So remember that it is kangaroos, hop down, mountains, drinking, chocolate, milk. This is our base unit. It represents meters or grams or liters or anything else we wanted to put in there, amps or candelas or moles, whatever. It's just a base unit. These are typically the ones that we use. All right. Notice something else. Notice that deca is a big D, whereas deci is a little d. The little letters, these letters, become little letters, all right, and these are capital letters. And that tells you that these are, this is 1, so these numbers are greater than 1, have a value of greater than 1, and these have a value of less than 1. All right, so if we were to do some conversion problems, let's say we wanted to know we had 2.3 kilometers, and we wanted to know how many meters is that. So we're going to go from kilo to the base unit. Well, what do we know about that? How many meters are in a kilometer? 1 kilometer is equal to, and we just count the hops. 1, 2, 3, 10 to the 3 meters. So 2.3 kilometers is 2.3 times 1, or 2.3 times 10 to the 3 to get meters. So here's how we're going to do it. This is called dimensional analysis. We're going to set up our problem like this. We're going to use our ratio, our relationship of kilometers to meters, and we're going to draw what we call a picket fence. Okay? I want my units to cancel out. We're basically multiplying by a fraction, and that's the ratio. And so I'm going to put kilometers on the bottom and meters on the top. That way my units cancel out and I'm left in the unit that I want to go to. And here's what I'm going to say. What's the relationship between kilometers and meters? Well, we know 1 kilometer has 10 to the 3 meters. Kilometers cancel out and I'm left with meters, and that would be 2.3 times 10 to the 3 meters. And actually the answer would be good enough. In scientific notation, no problem, but let's change it to regular notation, and that would be 2300 meters. 2,300 meters. Okay? So that's how you go from a larger unit to the base unit. Well, let's say we wanted to go the other direction. Let's say instead we're going to do, let's say we have 427 centimeters, and we want to know how many hectometers that is. So what's the relationship? Well, let's look at it. We'll start with the bigger unit, and we're going to say 1 hectometer, because I put the 1 on the bigger one, is equal to how many centimeters? Well, let's count. We're going to go from hecta to centi, so we're going to count. 1, 2, 3, 4. So that tells us, because it did 4, they're 4 steps away from each other, that there are 10 to the 4 centimeters in a hectometer. So now I'm going to use that relationship, and I'm going to say 427 centimeters times 10 to the 4 centimeters in 1 hectometer. And I'm just going to see my units cancel out, so I'm correct in the setup. My larger unit has a 1, which means I'm correct in my ratio. And now I just have to do the math. 427 times 1 divided by 10 to the 4. So without a calculator, that would be 427 times 10 to the negative 4, or divided by 10 to the 4. When you bring this up to the numerator, it becomes a negative exponent, and now I can either just plug that in my calculator, or I can do the math in my head, and I can say that that is, move this decimal over, 1, 2, 3, 4. So that would be 0.0427 hectometers. Alright, make sure you put units on everything so that we know exactly what your answer is. You can plug this in your calculator and it would give you this number, or if your calculator is set in scientific notation, that would be 4.27 times 10 to the negative 2 hectometers. Same answer, both of those are equivalent, and both of them are acceptable. Alright, so your worksheet that you're going to do in just a minute is going to be on practicing with metric conversions and practicing with dimensional analysis, which means dimensional analysis means setting up your problems like this with these, they look like picket fences. Some people call them field goal posts, because if you put another line right here, it looks like a field goal post. Sorry. Anyway, you need to, on a separate piece of paper, show all your work so we can see where how you're doing and make sure that you guys are doing what you need to do as far as the math. Alright, so that's one of the things that you're going to do in just a minute. The second thing that I'm going to have you guys do is a quick worksheet on significant figures. All right, so significant figures are significant digits, or something called sig figs. Usually I call them sig figs. Tell us how accurate a measurement is, because rulers can only measure things to a certain point, and graduated cylinders can only measure things to a certain point. So we have to keep in mind how accurate our measurement tool is, and that contributes to our math. The one with the least accurate measurement is going to tell us how many sig figs we're going to have. So we need to look at sig figs and figure out how many sig figs the measurement has. So here's a couple of rules on significant figures. And the one that causes you a problem are your zeros. Every non-zero digit is significant. So if it's a 1 through a 9, whatever, it's a significant digit. Where the problems come in are your zeros. Zeros are your problems. So here's a couple of rules. Zeros between non-zeros are significant. Sandwich zeros is what I call those. All right. So if I looked at a number, let's say I measured the mass of something, and it was 432 grams. Well, all of those are non-zero digits, so that means this number has 3 sig figs, because they're all non-zero digits. If I measured it and it was 402 grams, it would still have 3 sig figs. Why? Because this is a sandwich zero. It's between non-zeros, which means it's significant too. What does that mean by being significant? Well, that tells us that we measured this actual number. We actually measured the 2. And our scale told us the 2. It wasn't a rounded number. It wasn't, something that we guessed at. We actually measured the 2 here. So both of these numbers have 3 sig figs. So all non-zero digits are significant. Zeros between non-zero digits are also significant. Okay. Zeros in front of the first non-zero digit are not significant. Sometimes you see a number written like this. Well, that doesn't change the value of this. This still says that it is 3 sig figs. All right. Now, where else does that come into play? Well, here's where it comes into play. What if our number, our measurement, was 0.012 grams? This number would have 2 sig figs. This 1 and this 2 are significant. This 0 in the front of a non-zero digit is not significant, and neither is this one. It's a placeholder, and it does contribute to the value, but it doesn't contribute to the accuracy of the measurement. So we would say that number has 2 sig figs. All right, speaking of decimals, here's where decimals come into play, because you have to look at zeros after your non-zero digits. So zeros in the front are not significant. All right. Now the question comes, well, what about zeros in the back? If there's no decimal point, zeros that follow the last non-zero digit are not significant. I need to fix that on my PowerPoint. Are not significant. All right. So let's say this was your number, 1,000 grams. All right. How many sig figs are in there? Well, there's one non-zero digit, the 1. These zeros are not sandwiched. All right. And so since there's no decimal point, the zeros that follow the last non-zero digit are not significant. That means this number has 1 sig fig. Well, why does it only have 1 sig fig? Do we know that we measured exactly 1,000? What if it was 999 grams and just rounded up? What if it was 750 grams? Just rounded up. We don't know exactly if these were all accurately measured, so we only have 1 sig fig. let's change it up. Let's say it does have a decimal after it. So 1,000 grams with a decimal. That decimal tells us that we accurately measured that 0, and that changes that 0 to be significant, and therefore all these zeros are significant. And so therefore this one has 4 sig figs. Alright. So what about a number like this? 0.01020. Alright, so what do we know? Let's talk about our sig figs. We know all non-zero digits are significant. So that 1 is significant, and that 2 is significant. Okay? We know zeros between non-zeros are significant. So there's a sandwich 0, so that 0 is significant. Alright, zeros in front of the first non-zero digit are not significant. So these 2 zeros are not significant. And there is a decimal point. So since there is a decimal point, zeros that follow the last non-zero digit are significant. That means this one is significant. Therefore, this number has 4 sig figs. Alright, so to finish, we're going to make sure that we study for our our element quiz, and we're going to make sure that we finish up this worksheet. So do the metric conversions and do the sig figs, and you guys will have an element quiz on Wednesday, and we'll actually be going in the lab and doing a lab on Wednesday. So I will see you guys on Wednesday. Thanks.